In this video, I would like to talk about the evolutionary structure optimization (ESO) algorithm. We are going to input a geometry. In this example, it's going to be a box, and we are going to define some gravity points on it. In this example, I use this ramp ladder, which are shown as red, and this kind of rock placing here and there. And we are also going to define the bases, which are shown to be green. The bases should be think of as the pillar of the building. And the gravity points is going to just a point has has some super strong forces. And we are going to run the algorithm to shape our structure like this. So the resulting structure is kind of defined by our gravity points and the bases, which is kind of an interesting algorithm. So let's see it. The first thing I'm going to do is use a box. This will be our input. Use points from volume and connect adjacent pieces. What I'm doing here is just connect this point to add a line to here to its adjacent neighbors. And the idea is to put this structure into the Fathom solver. And if I set a point to have a great gravity, in the Fathom solver, we can calculate the stress for each of the constraints. The gravity, the force can propagate between these lines. So that's why we are creating this line structure. And I'm going to define my ladder and selecting my gravity points just by using the group, and these points will be the gravity points. So I set it as the force group. I also set the pin group, which will be the base underneath our structure. And then we simply use a solver. Let's jump inside. The first thing we do in the solver is to, for every one of the force point, we add a force to it. And then we create a balance constraint between each of, just create a balance constraint in our input geometry. It will be the distance along edge. And for the pin, that is the base, we set the mass to be 0. So we make sure that the balance will treat it like an infinite amount of mass object. And we use Fathom solver. Our goal is to calculate the stress by using the Fathom solver, so we can visualize the stress distribution. In the Fathom solver, we have to increase the constraint iteration to a very high number, so we can calculate the stress propagation properly. So you can see that the stress points, the forces will be propagated along these lines. And also, because I'm putting this Fathom solver into a solver, what I wanted to do is for each of the time step, for each of the frame, I wanted to re-simulate the Fathom solver. So we set the simulation type to be quasi-static. That is to say, no frame-to-frame coherency is present. The final result becomes that frame's result, okay? And then once we have calculated the stress, we might blur it. Let's visualize the result. And what I'm going to do is to remove the geometry that has small stress. So we simply use the delete node to remove the points that has small stress. I sort the stress and I simply remove some points. So after this step, we see some of the geometry is removed. And we can simply run this over many times. This will be the second step. So let's run it to the next frame. You see some of the geometry is removed because they have the least stress. So after the simulation, this is basically what we have. You can simulate the result. We will create this kind of structure. And we can just say using the points lab to use to construct a geometry from it. Kind of like this. Yeah, so that's basically it. The evolutionary structural optimization algorithm. The idea is very simple. We prepare our input. Basically, it will be a grid with a constraint connecting to its nearby neighborhood, and we're going to define the force points and the base points. And we just use develop to simulate the stress. And once we calculate the stress, we can simply remove the points that has small stress. So yeah, that's basically it.